So in terms of what the induction machine, upon the application of a three-phase voltage source on the stator winding, in terms of a three-phase induction machine, do you get it? A flux will be generated internally, which will rotate in the air gap. You know that there's a separation between the rotor or the armature. Armature is in terms of what? The DC. But this one, in terms of the rotor and that of what the stator, a rotating magnetic flux will be created. And that flux will cut across what? The rotor windings. Do you get it? That flux will cut across the rotor windings, and that one will induce a voltage in the what? In the rotor winding. Therefore, the principle of operation of an induction machine is the same as what? A transformer. So induction machine is called induction because the rotor voltage, which produces the rotor current and the rotor magnetic field, is induced by the what? Rotor winding, rather than physically connected by wires. Three-phase induction motors. So in terms of these lectures, we are considering what? The three-phase induction motors. In terms of the single-phase induction motor, it will be covered later in your preceding courses. There's a particular course called Special Electrical Machines. You will treat that one. In terms of single-phase induction motors, like the ceiling fans, it cannot start automatically unless you actually what? Do something to the the stator winding. Do you get it? We're having something called a starting winding. You need to provide a starting winding to the single-phase induction motors in such a way that it will be able to what? Operate. But in terms of the three-phase induction machines, upon the application of the three-phase current to the what? Terminals of the stator, a rotating magnetic field. Do you get it? Start instantly. And as the rotating magnetic field rotates within the what? The air gap, it cuts across the rotor windings. It will cut across the rotor winding, and upon the flux, rotating magnetic flux cutting across the rotor winding, it will induce a voltage in the rotor winding. And most induction machines, the rotor is actually shorted at the end. As a result of that, a very high current will flow in the what? Rotor windings. And as the high current flow through the rotor winding, according to Faraday's law of electromagnetism, anytime an electric current flows through a conductor or a coil, an EMF or a magnetic flux will be generated. Do you get it? So upon the current flowing through the rotor winding, it will also become a magnet. It will generate another magnetic flux. Do you get it? Which will try to chase the rotating magnetic flux, the one generated by the stator. Do you get it? So in chasing the rotating magnetic flux, it will finally lead to the rotation of the rotor. So that's how an induction motor operates. So these are the various advantages of induction motor. One, it has simple and rugged construction. It is relatively cheap. It requires little maintenance because in terms of induction machine, there is nothing like commutator. Do you get it? And in terms, we're having two types of induction machines. We are having the squirrel cage one and the wound rotor. In terms of squirrel cage, we don't use windings. The windings are in the form of what? Copper bars. I'll show you later. Do you get it? So that we don't actually require something like slip rings. You'll get to know the slip rings later. Slip rings are present in the the wound rotor induction machines. And another advantage, it has high efficiency and reasonably good power factor. It has self-starting torque. In terms of the three-phase induction machine, it has self-starting torque. Upon the application of the three-phase voltage at the terminal of the machine to generate the rotating magnetic flux, which will actually start the rotor, which will actually cause the rotor to rotate instantly. So it have a self-starting torque in terms of the three-phase machine. Disadvantages: it is essentially a constant speed motor, and its speed cannot be changed easily. So if you are actually using an induction motor in an operation where your main target is to vary the speed of rotation in terms of induction machine, when you go for induction machine, it is very difficult. But in terms of DC machines, their speed can be regulated easily. Do you get it? It requires a variable frequency power electronic drives for optimal speed control, unless you actually use power electronic converters. You get it? You have a variable voltage, variable frequency drives, power electronics. I believe you've been treated power electronics, or you can also use variable frequency drives. Do you get it? You can, unless you use those aspects, those power electronic stuff to regulate the speed. So constructionally, this is how the induction machine is made up of the stationary part. This stationary part is called the stator, and the rotating part, which is for the rotor. A three-phase induction motor has two main parts: the stationary part called the stator, and the revolving part, which is the rotor. So this is the stationary part. The rotor is separated from the stator by a small air gap. Do you get it? There's a space between the rotor and the what? The stator. Do you get it? In order to permit the revolution of the stator. So this is what the stator, and this is what the rotor. But in terms of the rotor, we are having two types of what rotor in induction machines. We're having the wound rotor and the squirrel cage induction motor. This is a typical example of the squirrel cage induction motor. As you can see from here, I would have wished to show you the squirrel cage. It is made up of what? A copper, or let's say an aluminum bar, aluminum plate. Do you get it? It's a core. Let me see if I can. Yeah, it's something like this. A metallic bar with these para slots. Do you get it? With these para slots, and they are shorted at both ends. As you can see, this is the short ending ring. It's like a ring which actually shorts. It's a ring which shorts the windings. So these are the windings in it. It is a bar. It's a plate. It's a metallic plate which are placed together in the slots, and the end of the metallic plates which forms the windings are what shorted by this ring. Do you get it? They are shorted by this ring. So this is called a cage rotor, a squirrel cage. Do you get it? This is a form of a cage. That's how come it is called the cage rotor. And we have the wire wound. So we have this is the cage rotor. And we have this is what the cage, and this is the wire wound. So the wire wound, it contains windings. There are windings in the rotor. Do you get it? There are windings in the rotor, and the ends of the windings. In terms of the three-phase, you need three windings. Do you get it? So they do wind the rotor in such a way that it will be in the form of a three-phase. So one end of the winding will be shorted, will be connected together. Do you get it? It will be shorted, and the other end needs to what? Connected to what? An external circuit. Do you get it? Through this rings. So these rings are called slip rings. These rings are called slip rings. Do you get it? For connecting the rotor to an external circuit. Let's look at something. So this is what the wound rotor. So the wound rotor have what? Slip rings. But the squirrel cage rotor do not have what? Slip rings. So two types of what? Rotor, which can place inside the stator. The squirrel cage induction motor, also called the cage rotor, and the wound rotor induction motor. Do you get it? Squirrel cage, the conductors would look like one of the what? Exercise wheels that squirrel or what? Hamsters run on. Oh, forget about this. So the squirrel cage rotor, it consists of a laminated cylindrical core having para slots. So these are the para slots. Do you get it? These are the para slots. So it consists of a laminated cylindrical core having parallel slots on its outer periphery. One copper or aluminum bar is placed in each slot. So these slots will house either a copper or an aluminum bar, as seen from this picture. All these bars are joined at each end by metal rings called end rings. So these are the end rings which connect the bars. Do you get it? And this form a permanently short-circuited winding, which is indestructible. It has a remarkably simple and robust construction, enabling it to operate in most adverse circumstances. It suffers from the disadvantage of low starting torque. In terms of an induction machine, the rotor circuit, if it has a very high impedance or resistance, it should be a resistance. If in case the rotor circuit has what a very high what resistance, do you get it? Its starting torque will become very high. It will have a high starting torque, but in a situation where the rotor resistance has what a low resistance, do you get it? The starting torque become minimum. So in terms of what the induction motor, the squirrel cage induction motor, there is no way you can either increase or decrease what the resistance. Do you get it? The rotor resistance, since it is made of what? This squirrel cage. No, this is the one rotor. Since it is made of what? The squirrel cage, and there is no circuit which can enable us to connect what? The rotor resistance or the rotor winding to an external circuit. Do you get it? But in terms of the one rotor, there's a circuit which was the slip rings, which will actually enable us to connect a variable what resistor or rheostat to through an external circuit. Do you get it? And with the help of what the rheostat connected to what the rotor through the slip rings, and bear in mind every end of what every phase of what the rotor winding is connected to a particular what slip ring. So we're having three phases, therefore definitely we'll be having what three slip rings. Do you get it? So we can connect an external resistance to a particular slip rings where we can regulate the resistance of what the rotor winding, and upon regulating what the resistance of the rotor winding, we can regulate the starting torque of the induction machine. So in terms of the squirrel cage, it suffers from the disadvantage of what? Low starting torque, simply because we cannot regulate the rotor resistance. It is because the rotor bars are permanently short-circuited, and it is not possible to add any external resistance to the rotor circuit to have a large starting torque. So in terms of the one rotor, this is how it is. It is wounded in such a way that you get a three-phase. And bear in mind that the ends of the winding are shorted, are connected together in the form of a star. Do you get it? The end of the winding are connected together, and the other end are connected to the various slip rings, where we can actually connect an external resistance to vary the resistivity or the resistance of the rotor windings. So it consists of a laminated cylindrical core and carries a three-phase winding. The rotor winding is uniformly distributed in the slot and is usually connected in three-wire. Why? The star. But as I said, if you remember, I said that the end of the three-phase winding are shorted together, are connected together. By so doing, we are connecting the rotor winding in star. Do you get it? The terminals are connected to three slip rings. So the terminals, the other ends are connected to these slip rings. These are called slip rings. But in terms of the cage rotor, there is nothing like slip ring. So internally, this is how the connection of a one rotor looks like. So there's one winding, two winding, three phase. Do you get it? So the end are shorted together to form the Y. Do you get it? And the other ends are connected to an external circuit through slip rings, through a variable resistor. And these are brushes, carbon brushes, and the carbon brushes actually sit on the slip rings, deliver the power toward the slip rings. So let's look at something. Induction motor construction. Cage induction motor rotor consists of a series of conducting bars laid into slots carved in the face of rotor. I've already explained all these things. So principle of operation of an induction motor. The most relevant aspect is for you to provide a power source to the stator. In an induction motor, it is a three-phase. We are considering the three-phase. Do you get it? If you want to operate an induction motor, just connect the three-phase with the three-phase winding of the stator to a balanced three-phase power source. Do you get it? And upon the application of the three-phase voltage source to the stator winding, the three-phase stator windings, automatically it will generate a rotating magnetic flux, which will be rotating at the synchronous speed. The rotating magnetic flux will be rotating at what? The synchronous speed. Do you get it? And upon the rotation of the magnetic flux through the air gap in the stator, through the air gap, it will definitely cut across the rotor winding. And bear in mind, the end of the rotor windings are short-circuited. The end of the rotor winding is what? Short-circuited. It's shorted. You get, as a result of that, it will permit a very high current to flow through the what? The rotor winding. And according to Faraday's law of electromagnetism, according to Faraday's law of what? Electromagnetism, anytime current flows through a coil or a conductor, a magnetic flux will be generated around the what? The flux. So upon the what? Current, upon the high current flowing through what? The rotor winding, the rotor will become a magnet. It will also generate a rather magnetic flux. And that flux will what? Will try to catch up with what? The rotating magnetic flux, which is actually rotating at what? The synchronous speed. But there is no way the rotor flux will be able to catch up the what? The rotating magnetic flux. You get it? So that one will finally lead to the rotation of the rotor. So that's how an induction motor operates. There's a speed difference between the what? The rotating magnetic field and the motor speed, the rotation of the motor speed. Do you get it? And that speed difference is called a slip. In induction motor, if the motor speed is the same as what? The synchronous speed, that means there is no way the motor will operate, because the motor speed needs to what? Lag the synchronous speed in such a way that the rotating magnetic flux, the internally generated rotating magnetic flux, will be able to what? Cut across the rotor windings to enable the what? Induction process to take place. If the motor speed is the same as the synchronous speed, there is no way the induction will take place. So in an induction machine, there is in an induction motor, there is a speed difference, and that speed difference is called a slip. That speed difference needs to be present in what? Induction machine before the machine will operate. So let's go through the principle of operation of an induction machine. First of all, energize the stator with three-phase supply. Current produced in the stator winding produces a rotating magnetic field in the air gap. This field revolves in the air gap. Do you get it? So the stator magnetic field links the rotor conductors through the air gap, and voltage will be what? Induced in the rotor conductors. Due to the fact that the rotor windings are short-circuited for both squirrel cage and one rotor, and induced what? Current flows in the rotor windings. According to Faraday's law of electromagnetism, currents in the rotor conductors will produce their own magnetic field. Do you get it? Which opposes the stator magnetic field. The torque developed due to interaction of the stator and rotor magnetic fields pushes the rotor into what? Rotation, because there will be two magnets. The one produced by what? The stator, and the one produced by what? The rotor. As a result of that, there will be repulsion and what? Attraction, according to the law of what? Magnetism. Like poles, when they come together, they will repel each other. And unlike poles, when they come together, they will attract. Do you get it? So the positive pole, let's say the what? The north pole of what? The rotor magnet will come into contact with what? Will approach the north pole of what? The stator magnet, and it will repel it. The south pole of the stator magnet will try to what? Attract the north pole of the what? Rotor magnet. Do you get it? And there will be repulsion, attraction, but there is no way they can attract. Do you get it? So the repulsion and attraction which takes place in the air gap will lead to what? Will finally lead to the rotation of the rotor. The torque developed due to interaction of the stator and rotor magnetic fields pushes the rotor into rotation. The direction of the rotation of the rotor is the same as the direction of the rotation of the revolving or the rotating magnetic field in the air gap. And bear in mind, we can, in terms of induction machine, when most of the time the direction of rotation is counterclockwise, you can definitely change what the direction of rotation. How can you do unless you just change the connection, the three-phase supply? Like you have A, B, and C. When you just change A and B or C, you will definitely change the what direction of rotation. So instead of the machine rotating counterclockwise, it will rotate in the clockwise direction. So the induction motor concept, the speed of the magnetic field, rotating magnetic field, the rotating magnetic field rotates with what? The synchronous speed. And synchronous is given by 120 Fe over P. This is the formula for the synchronous speed. The synchronous speed is given by this relation, 120 Fe, where Fe is the what? System frequency. And synchronous is what? The synchronous speed. And it's measured in what? RPM. P is the number of poles. So when you know the number of poles and the system frequency, when you know the number of poles of what? The stator. You get it? We can have 4 poles, 2 poles, 6 poles. When you know the number of poles of the stator, you can definitely calculate for what? The synchronous speed. This equation shows the what? Synchronous speed. Shows that the synchronous speed increases with what? Frequency, because it is directly proportional to what? The system frequency, and decreases with what? The number of poles, simply because the synchronous speed is inversely proportional to what? The number of poles. The three-phase of voltages has been applied to the stator, and three-phase set of stator current is flowing through the stator windings. Do you get it? The current produces the magnetic field according to the law of what? For this law of electromagnetism, anytime current flows through what? A conductor, it will produce a magnetic field. Do you get it? So the three-phase voltage source supplied to what? The terminals of what? The stator windings will cause three-phase current to flow through the stator windings, and those currents will produce what? The rotating magnetic field. Do you get it? That field is given by what? Bx is depicted as what? Bx. Rotating counterclockwise direction. Most of the time, the speed of rotation, the direction of rotation of what? An induction machine is what? Counterclockwise, anti-clockwise direction. Do you get it? But you can just change any of the what? Terminals, the phases, to cause the induction machine to rotate in what? The clockwise direction. Induction motor speed. At what speed will the induction motor run? There is no way the induction motor can run at what? Synchronous speed. Do you get it? There should be a slip. There should be a difference in speed. In speed. The difference in speed is what? The synchronous speed and the motor speed. Do you get it? In such a way that there will be an induction in the rotor coil. Because when the motor speed is the same as for the synchronous speed, there is no way an induction will take place. Can the induction motor run at the synchronous speed? There is no way the induction motor can run at the synchronous speed. Why? If rotor run at the synchronous speed, which is the same speed of the rotating magnetic field, bear in mind that the rotating magnetic field ran at what? The synchronous speed. Do you get it? So have that in mind. Just a minute. So if rotors run at what? The synchronous speed, which is the same as the speed of rotation of the magnetic field, then the rotor will appear stationary to the rotating magnetic field, and the rotating magnetic field will not cut the what? Rotor. So no induced current will flow in the what? Rotor. When the speed fall, okay, you can just go through there. I've explained everything. So the concept of rotor slip, the difference in speed, is called the slip. There should be a slip before the induction machine will be able to operate. Therefore, induction motor will always run at a speed lower than the synchronous speed. The rotation of what? The rotor. The speed of rotation of the rotor will be lower than the synchronous speed. The difference between the motor speed, rotor speed, and the synchronous speed is called the slip. N slip. This is N slip. N slip is equal to what? N synchronous minus what? Nm. Do you get it? N synchronous, that's the synchronous speed minus Nm. Nm is what? The motor speed. The slip speed. Slip is what? The difference in speed. So the difference in speed is what? Synchronous speed minus what? The motor speed. Do you get it? So N slip. Slip speed of the machine. Do you get it? N slip is what? The slip speed of the machine. N synchronous, the speed of the magnetic field, Bs. Nm, mechanical shaft speed. That's the motor speed. The motor speed is what? Nm. Therefore, we define the slip, S, as what? The N slip over what? N synchronous times 100. There's the slip. It can be in the form of percentage or in per unit, the slip. Do you get it? So what is N slip? N slip is what? N synchronous minus Nm. So by substitution, you get a slip to be N synchronous minus what? Nm over what? N synchronous. So this is the formula for the slip. Remember that this speed is in what? RPM. You can just convert it into what? Radians per second. And upon the conversion into what? Radians per second, you can represent the what? The slip in the form of what? Omega, angular velocity. So let's look at something. They are saying that just some few minutes. Okay, let me just use this. So in terms of this, if the rotor turns at the synchronous speed, can you see the whiteboard? Can you see my whiteboard?
Sir, it's visible.
Yes, sir.
Okay.
Yes, sir.
Okay. So let's look at something. So we've seen that the slip is equal to what? The slip is equal to what? N synchronous minus what? Nm over what? This is the reason why I wanted us not to meet online, because online we are not having the required material, so we do suffer a lot. Over ns. Do you get it? So this the synchronous speed in per unit, but it can be in the form of what? Percentage. Therefore, by multiplying this side by what? Multiply through the equation by what? Ns, you get what? The slip times what? Ns to be equal to the Ns minus what? The motor speed. No, the motor speed. The motor speed, which is what? Nm. So that means I need to dictate. I cannot write. Ns minus motor speed, making the motor speed the subject. Because if you know the synchronous speed and the slip, you can just calculate for what? The motor speed. Do you get it? Making the motor speed the subject, you get what? Or making Nm the subject. Making the motor speed the subject, you get Nm to be equal to this speed, Ns. Ns minus what? X Nx. Nx. And you get Nm to be equal to Ns is here, Ns is here. So Ns out, synchronous speed out into 1 minus what? S. Do you get it? So if you know the synchronous speed and you know the slip, you can just calculate for the motor speed using this relation. Nm is equal to what? Ns into bracket 1 minus what? S. I believe you are okay. So you can just calculate the motor speed using this relation. The same thing applies to what? The omega. This is speed in what? RPM, speed in what? Radians per second. These equations are useful in the derivation of induction motor torque and power relations. So keep note of that. Keep note of these equations. The induction motor works by inducing voltage and current in the rotor of the machine called a rotating transformer. So that is what the electrical frequency on the rotor. Bear in mind that in terms of electrical frequency, in terms of electrical transformers, the primary winding is different from what? The secondary winding. Do you get this? But in terms of a unit transformer, they are the same. The primary and secondary windings are the same. But in terms of step up or step down transformers, the primary winding is different from what? The secondary winding. As a result of that, the primary current and voltages are different from what? The secondary current and voltages. Do you get it? And also, in terms of the frequency, the system frequency, in terms of transformers, the primary frequency is the same as what? The secondary frequency. The frequency does not change. Induction machines operate the same as what? A transformers. Their mode of operation is the same as what? Transformers. The mode of operation of induction machine and that of transformers are the same. Do you get it? So, like a transformer, primary stator induces a voltage in the secondary rotor. Do you get it? In comparing induction machine with what? Transformers, the primary one is called a stator, the secondary one is called a rotor. Unlike a transformer, the secondary frequency not necessarily the same as what? The primary frequency. Do you get it? Because of the slip, because there's a slip, there's a difference in what? Speed. Do you get it? There's a difference in speed between the what? The motor speed and that of what? The synchronous speed. Because of that, the rotor speed is not the same. The rotor frequency is not the same as for the stator frequency. If the rotor of a motor is locked, so that it cannot move, that is stationary rotor. When you are locking it, that means you are preventing it from moving. Do you get it? Although you apply the voltage to the what? Terminals of what? The stator, but the rotor is locked. You are preventing it from what? Moving. Therefore, in a locked rotor, the motor speed is what? 0. But the synchronous speed is what? The synchronous speed. If the rotor of a motor is locked so that it cannot move, the rotor will have the same frequency as the stator. Because when the rotor is locked, the slip will be what? 0. When the rotor is locked, the motor speed will be 0. Therefore, we'll be having the slip to be what? 1. You get it? Look at something. When the rotor is locked, the motor speed is what? 0. So this parameter, omega m is 0. So we left with what? Omega synchronous over omega synchronous, and that will be what? 1. Do you get it? But the rotor's frequency depends on the slip. The rotor frequency is the same as the slip times what? The stator frequency. Do you get it? So when the slip is 1, in terms of what? Lock rotor, the motor frequency will be the same as what? The stator frequency. If the rotor of a motor is locked so that it cannot move, the rotor will have the same frequency as the stator. If the rotor turns at synchronous speed, when the rotor turns at the synchronous speed, let's look at the slip. When the rotor turns at what? The synchronous speed, that means omega m, the motor speed will be the same as what? The synchronous speed. As a result of that, what will be the value for the slip? Omega m minus what? Omega synchronous minus omega m will be 0, because the motor is now moving at what? The synchronous speed. Therefore, the slip will be what? 0. What will then happen? If the rotor turns at what? The synchronous speed, the frequency on the motor will be what? 0, because the slip is what? 0. For Nm equals what? 0. For Nm equals 0 revolution per minute, that is lock rotor. The rotor frequency is what? Fr equals what? The Fr, which is what? The rotor frequency, will be the same as what? Fe, which is what? The stator frequency. Simply because the slip is what? 1. When Nm is equal to the what? The synchronous speed, the rotor frequency will be what? 0. Fr will be equal to what? 0, simply because S is what? 0. Therefore, we can just develop a relation between what? With this in mind, we can just develop a relation between the rotor frequency and the stator frequency. The relation between what? The rotor frequency and the stator frequency will be given by this. Fr is equal to what? The slip times what? Fe. So if you know the stator frequency, which in Ghana is what? 50 Hz, and you know the slip, you can just calculate for what? The rotor frequency using this relation. For any speed in between, the rotor frequency is directly proportional to the differences. For any speed between 0, lock rotor condition, and 1, the motor rotating at the synchronous speed. For any speed in between, the rotor frequency is directly proportional to the difference between the speed of the magnetic field and synchronous and the speed of what? The rotor, Nm. That is the slip. They are trying to define the slip. So since the slip of the rotor is defined as this, slip is what? N synchronous minus Nm over N synchronous in terms of per unit. Then the rotor frequency can be expressed as F rotor is equal to what? The slip, which is this, times Fe, the theta frequency. Fe is the theta frequency or the system frequency. Therefore, by substitution, F rotor will be equal to the slip, which is this. The whole of this is the slip. Do you get it? Times Fe. This is Fe. Do you get it? And upon what? Let's look at something. N synchronous. The synchronous speed is given by this relation. Let's look at something. N synchronous minus. Okay. Look at something. We just shift this part here. Do you get it? This part, N synchronous minus what? Nm is this part. Over what? The synchronous speed. But we know that the synchronous speed is given by 120 Fe over P. Do you get it? This synchronous speed, 1 over the synchronous speed, is, you know that the synchronous speed is what? 120 Fe over P. Do you get it? By this equation, in terms of this, you'll be left with what? 1 over the synchronous speed. So we need to multiply this side by the reciprocal of this equation. Do you get it? That's how come we got what? P over 120 Fe to cater for this part, over the N synchronous part, times the Fe. Do you get it? And bear in mind, the Fe will cancel this Fe. Do you get it? And we'll be left with what? Fr, the rotor speed, to be what? P over 120 all into what? N synchronous minus Nm. Where Fr is the what? Frequency of what? The rotor frequency, and Fr is the theta frequency. The torque. Why? We know that the torque, load torque, this is called load torque. In terms of load torque, the output power relates with the load torque by what? The load torque times what? Omega m. PR is equal to what? Load torque times omega m. We know that omega is what? 2 pi omega m. The speed of what? The motor in omega is 2 pi nm. Nm is in what? Radians per second over 60. You know of this equation already. Why the input to the induction motor is electrical power, its output is what? Mechanical power. Do you get it? In terms of induction machines, in terms of electrical motors, the main job of what? An electrical motor is to convert an electrical energy into what? Into a mechanical energy. Do you get it? So the input of induction motor is what? Electrical energy. The output is what? Mechanical energy. So the input is mechanical power, electrical power. The output is what? Mechanical power. So we need to know what the relation between mechanical power and electrical power. But in terms of mechanical power is given by what? Torque times omega. That one is what? Mechanical power. Why the input to the induction motor is electrical power, its output is mechanical power. And for that, we should know some terms and quantities relating to mechanical power. Mechanical power is torque times omega. Any mechanical load applied to motor shaft will introduce a torque on the motor shaft. This torque is related to the motor output power and the rotor speed. So it's given by this relation. So the load torque is given by this relation. Horsepower, most of the times we are having horsepower. In mechanical, we deal with what? Horsepower. And there should be a relation between what? Horsepower and what? Watts. In electrical, we deal with what? Watts. But in mechanical, we deal with what? Horsepower. Let's say a particular machine is rated 5 horsepower. You should know the correspondency between what? Horsepower and watts. In power system, in electrical and mechanical, 1 horsepower corresponds to what? 746 watts. So you should know this conversion. Another unit used to measure mechanical power is the horsepower. It is used to refer to the mechanical output power of the motor. Just a minute. Let me look at something. Attendance. Admit all. 30. Okay. Let's proceed. See the impact of the online class. Only 30 participants. I believe you can see my screen now. Can you see my screen?
Yes, sir.
Okay, so let's go. Another unit used to measure
Yes, we
mechanical power
can
is the
see your
horsepower.
screen.
It is used to refer to the mechanical output power of the motor. Please mute yourself. Mute yourself. Mute your microphone. It is used to refer to the mechanical output power of the motor. As electrical engineers deal with what? Watts. As a unit to measure what? Electrical power. There's a relation between horsepower and watts. So there's the relation. So 1 horsepower corresponds to what? 746 watts. So let's solve this example. A 208 volts, 10 horsepower, 4 pole, 60 Hz, star connected induction motor has a full load slip of 5%. The slip is what? 5%. So in per unit, you just divide by sorry. The slip is given by 5, given as what? 5%. So you just divide by 100 to get the slip in per unit. So these are the parameters. What is the what? Synchronous speed of this motor. The synchronous speed is given by, and the synchronous speed nx is given by what? 120 fe over p. So 120 times what? The system frequency, which is what? 60 Hz over p. How many poles? 4 pole over 4 will give you the synchronous speed. What is the rotor speed of this motor at rated load? I should calculate this, but I cannot. So I'll just tell you how to go by it. What is the rotor speed of this motor at rated load? What is the rotor speed of this motor at rated load? Know that there's a relation between the motor speed and the what? The synchronous speed. When the slip is known, the motor speed relates the synchronous speed with this relation. Do you get it? Nm is what? 120 minus 1 minus x times the synchronous speed. So after calculating for the synchronous speed, you can just calculate for the motor speed by using that relation. So Nm will equal to what? 1 minus what? S. The slip is what? 5%. 5% is the same as what? 0.05. So 1 minus 0.05 times the synchronous speed. Do you get it? So in terms of this, the synchronous speed will be 4 poles will be 1,800. In Ghana, we are using 50 Hz. Our synchronous speed is what? 1,500. But in 60 Hz, to be 1,800. So the third one, what is the rotor frequency? You know the slip. Do you get it? The rotor frequency is what? The rotor frequency is given by this relation. Frequency of the rotor, the slip times what? The electrical frequency. So use this to calculate for the rotor frequency. By so doing, you'll be able to calculate for the rotor frequency. What is the shaft torque? The power is rated at what? 10 horsepower. 10 horsepower. So you know the power. But we know that torque is what? Torque, the shaft torque, that is the load torque. Torque is what? Power is what? Torque times what? Omega. Power is what? Load torque times what? Omega. That's the omega m, not omega s, because we are dealing with what? The shaft torque. The shaft torque is the what? Motor speed. This is what the motor speed. Do you get it? So you need to calculate for omega m. But you'll be able to calculate for what? The motor speed in RPM. Therefore, you need to convert what? The motor speed into what? Radians per second. You divide the motor speed in radians per second. You divide what? The 10 horsepower by the motor speed in radians per second. And you'll be able to calculate for what? The shaft torque. So these are the calculations. The synchronous speed. 120 times Fe over P. 120 times what? The 60. Which is what? The system frequency over P. The number of pole. and you get 1800 RPM. The motor speed is 1 minus x ns. 1 minus the slip. The slip was given as what? 5%. So you divide by 100. 1 minus s times the synchronous speed. You get the what? The motor speed in radians per second. The rotor frequency, slip times the system frequency or the stator frequency, 0.05 times 60, which will give you what? 3 Hz. The load torque, or the shaft torque, you get it, the same as the load torque, because the load is actually connected at the shaft of the what? The motor. Do you get it? So the load torque is the same as what? The shaft torque. It's equal to the output power, P out over omega m, the speed of the motor. But what is the output power? 10 horsepower. By 1 horsepower is what? 746 watts. So we multiply by 10. All over 1710 times 2 pi over what? 60. You convert the what? The motor speed in RPM into what? Radians per second. And you arrive at 41.7 Newton meter. Thank you. So let's move on. So this is what the equivalent circuit of an induction motor. Just a 2-minute break and we continue. 2 minutes, don't go anywhere. I'm just around. So let's start. Can you see the screen?
Yes, sir.
Okay, so let's continue. So the equivalent circuit of an induction motor. Bear in mind, the equivalent circuit of an induction motor is approximately the same as what? That of a transformer, a power transformer. Just that there's a slight difference. So let's go through. A transformer model. Model of the transformer action. Induction of voltages and currents in the rotor circuit of an induction machine is essentially a transformer. Do you get it? Because the rotating magnetic flux will actually cut across the rotor windings and that will induce a voltage. The same principle as the operation of what? Power transformers. The same. As in transformer model, certain resistance, self-inductance in primary or stator windings, magnetization curve, and etc. Okay. The rotor circuit model, the greater the relative motion between the rotor and the stator magnetic field, the greater the resulting rotor voltage and frequency. Block rotor, forget about this. The equivalent circuit of what? A transformer. Let's move ahead and see. So this is the overall equivalent circuit of an induction machine. It is the same as what? A transformer. If you do remember transformers, the equivalent circuit of a transformer, there's the primary side and this is what? The secondary side, and we have what? the ideal transformer in between. These are the windings. Do you get it? So these are the windings. So these are the various definition terms. Do you get it? Various parameters. The parameters. These are the definitions. In terms of transformer, stator winding, the primary winding resistance, primary winding inductance. Do you get it? So this is what an induction machine. So this R1 is what the stator resistance. X1 is the stator leakage reactance, and what IM is the magnetizing current. This current actually takes place in the air gap. Or do you get it? Because between the stator and the rotor, there's a gap. That gap is called the air gap. The RC is what the core losses. It takes care of what the core losses. RC resistance losses corresponding to iron losses, windage, and what friction losses. The core losses are covered by this RC. The hysteresis and the eddy current losses are all covered by the RC. XM, the magnetizing parts. The magnetizing parts is XM. Where is it? XM, magnetization reactance. So this E1, do you get it? The core, the voltage induced at the core. At the what? The stator winding. ER is the voltage at the what? The rotor winding. IR is the rotor current. Do you get it? XR, the rotor what? Reactance. RR, rotor resistance. So these are the various parameters. The equivalent circuit of an induction motor. The same as what? Almost the same as what? That of a transformer. So let's move ahead. The rotor circuit model. So now let's model the rotor circuit. Yeah, to model the rotor circuit. In terms of transformers, we have something like this, the equivalent circuit like this, where we most of the times we transfer the rotor circuit to what where we do transfer the secondary winding, the secondary circuit to the primary circuit. Do you get it? Based on the turns ratios. So we do the same for the induction machines, where we transfer the rotor circuit to the stator circuit. So let's go through that. The rotor circuit model. Suppose the motor ran at a slip S, meaning that there's a slip, there's a difference in speed, meaning that the rotor speed is ns into what? 1 minus s. We've already derived this equation, where ns is the synchronous speed. Then this modifies the value of voltage and current on the primary and secondary sides due to what? The difference in speed, and also as well as the frequency. The frequency of the induced voltage at any slip will be given by this relation. Assuming what? ER0. What is ER0? This is ER0. ER0, do you get it? At the stator part. Assuming that ER0 is the magnitude of the induced rotor voltage at log rotor. At log rotor, that means the slip is what? 1. At log rotor, the slip is what? 1. Therefore, ER0 will be the same as the stator. You know that ER0 is at the stator, corresponds to the stator. But when there's a log rotor, ERR will be the same as what? ER0, simply because the slip is what? 1. Assume ER0 is the magnitude of the induced rotor voltage at log rotor condition. The actual voltage induced because of slip is what? ER equals what? SER. When there's a slip, ER will be what? SER0. But when the slip is what? 0, in terms of what? Log rotor, ER will be the same as what? GR0. Okay. The resistance is not frequency sensitive. Let's look at something in terms of a resistance. It does not depend on what? Frequency. Do you get it? It is frequency independent. It is frequency independent. But in terms of the inductance and capacitors, do you get it? Capacitors and inductors, they do depend on frequency because they have omega. I know that omega is given by what? 2 pi f. There's frequency in what? Omega. capacitors and inductors, they have omega. Do you get it? Therefore, they are all frequency dependent. But in terms of what? Resistors, there's nothing like omega. So the resistor is not frequency sensitive. The value of what? RR remain the same. You are working on the transformation. You want to transform the you want to transfer the what? Rotor winding parameters to the secondary side. Do you get it? Now we know that the ER, the rotor side, the rotor voltage corresponds to SER0 on the what? The stator circuit. But since RR does not depend on frequency, RR will be the same as what? RR at the stator circuit. Okay. So the resistor is not frequency sensitive. The value of what? RR remains the same. The rotor inductance is frequency sensitive simply because X is what? Omega L, which is the same as what? 2 pi FL. Then XR is equal to what? XR0. Because the slip, the difference in slip, the difference in speed is what? The slip. And that slip depends on omega, angular velocity. Do you get it? And since the rotor inductance is frequency dependent, if you want to calculate for the corresponding rotor inductance at the stator winding, you just multiply by what? X. So JXR is the same as what? JXR0 at the what? The stator circuit. So the frequency of the voltages and currents in the stator is what? F. But the frequency of the voltage and what? Current in the rotor is what? SF. Do you get it? By the slip. So the overall equivalent circuit of an induction motor, the rotor circuit model. So the rotor circuit will be transformed in this form. Do you get it? The rotor circuit will be transformed. This rotor circuit will be transformed in this form. Do you get it? So this is the equivalent circuit of the rotor circuit. Let's look at something. How can we calculate for IR, the current flowing through the rotor winding? Is equal to what? The voltage ER. But now the ER is what? SER0. Do you get it? SER0 over the total impedance. What is the total impedance? The total impedance is given by JXR0 plus what? RR. Do you get it? So IR is equal to what? ER, this ER over RR plus what? JXR0. That's the total impedance. But IR is equal to what? SER0. That's the same as what? ER. Do you get it? Over RR plus what? JXR0. This. What can we do? We should see to it that the numerator part is what? Is ER0. So we need to what? Divide both the numerator and the denominator by what? The slip. And upon doing that, you arrive at ER0 over RR over S. Do you get it? Plus this over the S. The S will cancel the S. So we'll be left with what? JXR0. So this whole part, the denominator, is called the equivalent rotor impedance. The ZR equivalence, the equivalent rotor impedance of the induction machine. Keep note of this. RR by X, ER0, when it is being transformed to the secondary side. Do you get it? We are seeing to you that what have we done? We are transforming the what? The omega part, the slip, to the rotor side. Do you get it? Therefore, in terms of the overall equivalent circuit of an induction machine, when we transform, when we transfer the what? The rotor circuit to the stator side, the induced voltage at the what? Rotor winding will be ER0. That of what? The rotor inductance will be JXR0. But that of what? The rotor resistance will be RR over what? X. You need to divide the what? The rotor resistance by what? X, based on this. So you arrive at this. Do you get it? So the corresponding impedance value at the corresponding what the equivalent circuit of the rotor resistance, the rotor what circuit will reduce to this form. Do you get it? JXR0, ER0. This is the ER0, ER0, JXR0, JXR0, and the rotor resistance will be divided by the slip, same as this. The rotor circuit model with all the frequencies, slip effects concentrated in the resistor RR. So the equivalent circuit of an induction motor. This transformation we can just go through the transformation. In terms of the transformation, in terms of transformers, based on the turns ratio, we are able to transfer the secondary circuit to the primary circuit. The same thing applies to the induction machine. Do you get it? So this is the overall equivalent circuit of an induction machine. JX2 E1, do you get it? JX2 E1 R2 by what? X. Do you get it? The rotor side you divide by X. Right? Just the way that you'll be able to get rid of the ideal transformer part and the rotor circuit. So this is the overall equivalent circuit of an induction motor. So take note of this circuit. All our calculations, everything, all our derivations will be based on this circuit. So you should know how to draw the equivalent circuit of what? An induction machine, right? The rotor circuit model that will be referred to the stator side is as shown below. Do you get it? The rotor circuit model. So if you don't bring the X in the resistance part, you are doomed. Do you get it? So the per phase equivalent circuit of an induction motor. Bear in mind that in terms of the induction machine, we are considering what a three-phase system. Do you get it? But the phases are the same. Do you get it? So we just consider one phase. So this is a per phase equivalent circuit of what? An induction machine. Power and torque in an induction machine. In terms of an induction machine, we are having what? The stator part, the rotor part. And bear in mind that the power is connected to the stator winding. Who is that? So in terms of what? In terms of an induction machine, the stator winding is being supplied with a three-phase power supply or a power source. Do you get it? And from the stator winding, we move on to the air gap. From the air gap, before we go to what? The rotor. Do you get it? From the rotor winding, the rotor, most of the time the rotor, we do attach what? A bearing. A bearing is actually connected to what? The outer casing. Do you get it? In such a way that the rotor will be able to what? Revolve smoothly. Do you get it? So this is the power flow in an induction machine. You just connect a three-phase power supply to the stator winding, and the three-phase power supply is the input power, and the input power is given by root 3 VTIL cos phi. Do you get it? Or in terms of per phase, it will be 3 times V phase I phase cos phi. So is the input power which is being supplied to the stator winding. Okay, let's look at something. The stator winding has what? I square R losses. Do you get copper losses? So that one is designated by what? Stator copper loss. P stator copper loss. Do you get it? So the P in, you subtract what? The stator copper losses from the input power. You'll be left with the power at the core. Do you get it? And look at something. The stator winding are what? Impregnated in the core. Do you get it? Because in terms of the core, it is made up of what? Slots. And the stator windings are in the what? Core. Do you get it? The slots of the core. Do you get it? So after subtracting the stator copper loss from the input power, we'll be left with what? The power in the core. Do you get it? And after subtracting the core and the theta copper loss from the input power, you'll be left with the power at the air gap, because there is a separation between the rotor and that of the stator. Do you get it? And that separation is called the air gap. So when you subtract the core losses and the stator copper loss from the input power, you'll be left with the power at the air gap. And the power at the air gap is called PAG, air gap power. Air gap power. Do you get it? Okay, let's look at something. So it is the air gap power which causes the induction on the rotor. Do you get it? The air gap power is normally transferred to the rotor circuit. When the air gap power is being delivered to the rotor circuit, the rotor windings have what? Rotor copper losses. Do you get it? So when you subtract the rotor copper losses from the air gap power, you'll be left with the power, the converted power. And the converted power is at the shaft. Do you get it? The converted power is at the shaft of the rotor. Do you get it? But bear in mind, the rotor, there is what? There is bearing. Bearing is actually connected to the rotor in such a way that you'll be able to fix the outer casing. Do you get it? And that one, the bearing actually hold the rotor in place. There are two bearings at both ends of the rotor to hold the rotor in place in such a way that the rotor, the exterior portion of the rotor do not touch the interior casing of the stator, in such a way that there will be an air gap between the rotor and that of the stator. So the P converted is here as a result of the bearing in the as a result of the bearing connected to the rotor. There will be a friction losses and also windage losses, windage caused by wind. Do you get it? So you need to subtract the friction and windage losses from the P converted. Do you get it? When you are able to subtract the friction and windage losses as well as the stray losses or other losses. Other losses can be in the form of heat when they are actually provided in the question. You need to subtract them all from the P converted, and what you'll be left is the output power, P output, which will be used to power the load. Do you get it? So the P output is equal to what? The P in minus what? PAG minus what? P converted minus what? The friction and windage losses, and that of the stray losses. PXCL is the losses in stator windings. That's why it's same as for I square R. P core is the hysteresis and eddy current losses. The power flow diagram of an induction motor shows the relationship between the input electric power and the output mechanical power. That's the power flow diagram in an induction motor. Power and torque in induction motor. So the load torque can be found here, and the induced torque can be found at the P converted. So P converted is equal to T torque induced times omega n. Do you get it? So let's proceed. The whole of this is depicted here. It's the same as this. The input power, this is the stator, this is the rotor. The input power, the stator copper loss, the core loss, the air gap power. After subtracting the stator copper loss and the core loss from the P in, you will left with the air gap power. Same as this. Subtracting the stator copper loss and the core loss from the P in, you will left with the air gap power. So this was the air gap power. The air gap power powers the rotor circuit. Do you get it? And after subtracting the rotor copper loss from the air gap power, you will left with the P converted. Subtracting the rotor copper loss from the air gap power, you will left with the converted power. The P converted, and the P converted is the same as torque induced times omega m. After subtracting the friction and windage losses, as well as the stray losses from the P converted, you'll be left with the P output. Okay, 29. Chat. Let me see. So that is it. So let's continue. So let's look at something. P rotocopper loss. P rotocopper loss. What is it? The rotocopper loss. If you want the rotocopper loss, it's the same as the what? PAG minus what? P in. Or no. In terms of considering this part, P rotocopper loss is the same as what? PAG minus what? P converted. P rotocopper loss is what? PAG minus what? P converted. Because PAG, okay, P rotocopper loss is what? PAG minus what? P converted. This is P converted. This is PAG. Okay, so there's the relation for the P rotocopper loss. PAG is what? Torque induced times omega S, the synchronous speed, the air gap power. Because the magnetic flux will be rotating in the what? In the air gap. Do you get it? The rotating magnetic flux rotates in the air gap. Therefore, if you want to calculate for the what? The air gap power is the torque induced times the omega S. Do you get it? The synchronous speed. Right? The P converted is what? Torque induced times omega M. Torque induced times omega M. Therefore, P rotocopper loss is torque induced omega S, which is what? The PAG minus what? Torque induced omega M. Omega X omega M. Okay, torque induced. Making torque induce the subject. We'll be left with what? Omega X minus what? Omega M. We divide both sides. You divide this side by what? Omega X. And you multiply by what? Omega X. This X will cancel this. We will arrive at this same equation. But bear in mind that omega S minus omega M over omega S is what? The slip. Someone is trying to join. Participants. You get so the S is what? Omega S minus omega M over omega S. That is the S. Do you get it? So the rule of this should be replaced by what? S. So P rotocopper loss will be left with what? This S slip torque induced times this omega X. Do you get it? P rotocopper loss is now X torque induced times omega S. Right? But what is torque induced times omega X? Torque induced times omega X is the same as what? PAG. So X is what? X times what? PAG. So P rotocopper loss is the same as what? The slip times what? The air gap power. So if you know the air gap power and you know the slip, you can calculate for the rotocopper loss using this relation. P converted. The P converted will be what? The PAG from this relation. P converted will be what? PAG minus what? P rotocopper loss. PAG minus what? P rotocopper loss. Therefore, P converted will be what? PAG minus P rotocopper loss, which is the same as what? SPAG. Do you get it? Therefore, making PAG the subject, you will left with what? P converted, which is what? PAG into bracket 1 minus what? S. So if you know the what? PAG and the slip, you can calculate for the P rotocopper loss using this relation, and also the P converted using this relation. Bear in mind that the torque induced, the induced torque, is equal to what? The PAG using this relation, the PAG over what? Omega X. And also, in terms of the rotocopper loss relation, we know that the P rotocopper loss over X omega X, you can just go by this. P rotocopper loss is equal to what? PAG. So you divide by X. Do you get it? P rotocopper loss by S is the same as the PAG. Do you get it? So for substitution, you arrive at this. So you can just use this to calculate for the induced torque of the induction machine. So let's look at something. This is the relation, 1:1 relation. PAG is 1. P rotocopper loss relates with PAG by S. P converted relates to PAG by 1 minus S. So if you know the PAG and the slip, do you get it? P converted will be equal to what? PAG times 1 minus X. P rotocopper loss will be equal to what? PAG times what? S. Okay. The overall equivalent circuit of an induction machine is this. We've already derived this equation. Let's look at something. The I1, the current flowing through the entire circuit. The current flowing through this part, the terminal current. The current flowing through the circuit is given by this. According to Kirchhoff's current law, when I1 arrives at this junction, it was split. IM will flow this direction, I2 will flow through the rotor. So I1 is flowing through the stator and the rotor circuit. So how can we derive I1? I1 is equal to the phase voltage, the terminal voltage, over the Z equivalent. What is Z equivalent? The total impedance. As you can see, R1 and JX1 are in series. Do you get it? JX2 and R2 by S are also in series. RC and JXM, XM are in parallel. So Z equivalent is the series combination of R1 and X1, which is this, plus the parallel combination of RC and JXM, which is this, which is in parallel with the series combination of R2 by X and X2. So that is the equivalent impedance. So when you are able to calculate for Z equivalent and you know the V phase, I1 is equal to V phase over the Z equivalent. Separating the rotor copper loss and the power converter in an induction motor equivalent circuit. The overall equivalent circuit of this. In terms of the rotor side, the overall equivalent circuit of an induction motor is given by this. Look at R2 by X. The rotor resistance is given as by R2 by X. Okay. Separating the rotor copper loss. The rotor copper loss. If you want to separate the rotor copper loss and the power converter in an induction motor, you want to separate the rotor copper loss. You want to separate the rotor copper loss from the P converted. Do you get it? What do we need to do at the rotor side? We multiply this R2 by S by 1 minus X. Resistance equivalent to mechanical load, to get the mechanical load. If you want to subtract the rotor copper loss from the P converted to get the mechanical load, you just multiply this side. This side by 1 minus X, 1 minus the slip. Take note of it. Do you get it? So this R2 will be replaced by this. Separating the rotor copper losses and the power converted in an induction motor equivalent circuit. Part of the power coming across the air gap in an induction motor is consumed in the rotor copper losses. Do you get it? And part of it is converted to mechanical power to drive the motor shaft. Do you get it? So if you want the power which actually drives the mechanical load, by considering the rotor copper losses, you go by this. Do you get it? So this is resistance equivalent to mechanical load. All right. A typical example. Let's go through these examples. Go through this and this. Let me see. An induction motor drives 60 amps from a 480 volts. An induction motor draws 60 amps from a 480 volts, 60 Hz, 50 horsepower, 3-phase line at a power of 0.85 lagging. There's the power factor. The stator copper losses are 2,000 watts. Stator copper loss is given as 2,000 watts, and the rotor copper loss are 7,000 watts. The rotational losses include 6,000 watts of friction and windage, 1,000 watts of core, and negligible stray load losses. Calculate the following quantities. A, the air gap power, PAG. B, the power converted, P converted. C, the output power. D, the efficiency of what? The motor. PAG, when you are able to draw the power flow diagram. PAG, P in through stator copper loss and P core loss. From this, PAG, look at something. How can we get the power here? You know the input power, you know the stator copper loss, and you know the P core. Therefore, PAG will be what? The P in minus what? P rotor copper loss, P stator copper loss minus what? The P core. Do you get it? So by using this relation, P in, PAG is what? P in minus what? P stator copper loss minus what? P core. What is P in? An induction motor draws 60 amps from what? 40 volts, 480 volts. Do you get it? 60 hertz, 50 horsepower, 3-phase line. This is a line. Do you get it? 480 volts is a line. 60 amp is what the line current. Therefore, you can just calculate for the P in using this relation. P in is what? Root 3 times VT times IL. Therefore, the P in is what? Root 3 times VT. VT is what? 480 volts. Times what? IL. IL is what? 60 amps. Times cos phi. What is the power factor? 0.85 flagging. Do you get it? And you get your P in to be what? 42.4 kilowatts. We have to calculate for our P converted. No, the P air gap. Therefore, our PAG is P in, which is 42.4 kilowatts, minus P stator copper loss. Stator copper loss was given to be 2000 watts, so 2 kilowatts, minus what? P core, and the core loss was given as what? 18 watts. 18 what? 1.8 kilowatts. 18,000 watts. 1,800 watts rather. 1,800 watts of core. Do you get it? So you just subtract everything and you arrive at 38.6 kilowatts for the air gap power. So how can we calculate for our P converted? We should know the, if in case we know the slip, we could have actually calculated for the air gap power using this relation, the P converted using this relation, 1 minus S times what? The air gap power. But with this, we don't know the slip. The converted power, P converted is what? PAG minus what? P rotor copper loss, as seen here. P converted is what? PAG minus P rotor copper loss. Do you get it? P converted, PAG minus what? P rotor copper loss. So use this relation to calculate for our PAG, the P converted. So P converted is what? PAG minus what? P rotor copper loss. The PAG was calculated to be 38.6 kilowatts. What about the rotor copper loss? 700 watts. Look at something. And rotor copper loss are 700 watts. So this is the rotor copper loss. So you do substitution and you arrive at 37.9 kilowatts. The output power. So what is the output power? Is what? P converted minus what? P friction and windage loss minus what? P what? Stray. The stray losses. Do you get it? But the stray losses, according to the question, the stray losses are negligible. Do you get it? You just use the power diagram, the power flow diagram. Do you get it? The output power, P converted, P out is equal to what? P converted minus what? P friction and windage losses minus what? The P stray. You know the P converted, you know the friction and windage losses. So the P, this part is what? 0. P out is equal to what? P converted minus P friction and windage losses. So P out, P converted minus P friction and windage losses minus what? P stray. But the stray part is what? 0. So you'll be left with what? The friction and windage losses, which was given as 600 watts. So by substitution, you will get 37.3 kilowatt. This is the output power. How can we calculate for the efficiency? The efficiency is what? The output power over what the input power times 100 in terms of percentage. So the output power is what? 37.3 over what? The input power. And the input power was calculated to be what? 42.4 kilowatts. So 37.3 over what? 42.4 kilowatts times 100. Kilowatts will go, you'll be left with what? 37.3 over what? 42.4 times 100. So you arrive at what? 88% as the efficiency of the machine. Another question. So I'll just leave this question behind and we will solve this question in our next meeting. We'll solve this question in class. So any question? Thank you very much.